This is Conway's Game of Life, a cellular automaton created by John Conway in 1970. Cellular, meaning individual pixels, behave individually, like cells, from one iteration to the next. And automaton, meaning that the game is completely automatic. Once you define an initial condition, it evolves deterministically forward in time. The behavior of each pixel is algorithmic. I think a lot of physicists and mathematicians love this game as such an approachable example of how a small set of extremely simple rules can govern this amazing, rich, and complex emergent behavior, just like the real world. Many patterns in Conway's Game of Life die out pretty quickly, but some of them, even from a small starting configuration, can grow to become extremely complicated. This is what you get if you feed the game my favorite blockist tile, the R-pentomino. Everybody does have a favorite blockist tile, right? Like, if you don't have a favorite blockist tile, what are you doing? This pattern takes 1,103 iterations to stabilize, and once it has, it shot off a few patterns called gliders and expanded into a bunch of stable blobs that are either totally static or repeat with a short period. In contrast to the R-pentomino that explodes into a bunch of stuff, let's actually look at one of those gliders. If you set one of these up as an initial condition, you'll see that these patterns are much more controlled and actually exhibit some pretty complicated behavior. If I slow this down, we see that every 4 iterations, the exact same pattern is generated, but it's shifted diagonally. Cells in Conway's Game of Life cannot move. They can only turn on and off in place. But this looks like a structure that's capable of moving itself across the game board. It's periodically replicating itself, slightly translated. In general, though, the Game of Life is fundamentally hard to predict. If you have an ending configuration and a starting configuration of a group of cells, there's really no good way to connect those two without starting with the starting configuration and just running the simulation to see what happens. This is a very different kind of pattern that I very carefully constructed with literally weeks of compute time on my most powerful home computer. Unlike the other patterns, it actually shrinks from iteration to iteration until it reaches this stable configuration with multiple still lifes and 3 oscillators of period 2. Can you see the resemblance? At this point, most of the viewers on the channel are like, wow, big whoop, it made a pattern. How hard can that be? And a very small subset of you who have tried to make similar predictions, hopefully, are quite shocked. That was 21 steps backwards for those of you counting at home. And then an even smaller subset of the viewers of this video who, unlike me, are extremely familiar with the Game of Life, are probably looking at this and going, why didn't he do it some straightforward way by like running gliders into each other or something? It's really common for people to draw some recognizable pattern in Conway's Game of Life, click go, and watch that recognizable pattern turn into something that looks like random noise. Along the way, it turns into these cool blobby cell-looking things, which is really neat because the blobby shapes actually do resemble bacteria growing in a petri dish or something, but I want to do something a little different. I wanted to be able to produce a pattern that looked like random noise, but when you ran it through the Game of Life algorithm, actually produced something recognizable. Okay, so maybe this doesn't look super impressive. Taking forward steps in the Game of Life is trivial. How hard can it be to design a pattern and then compute the previous state, and then compute the previous state again, and then compute the previous state again? It should be easy, and that's what I thought 3 years ago when I started working on this project. I picked it up for, a little bit, like every 6 months when I had a new idea. I eventually came up with an algorithm that was able to take 21 steps backwards in 3 or 4 weeks of compute time. That final algorithm, weirdly enough, was actually single-threaded. So I could have made 12 patterns on that computer at once, or 16. How many cores does it have? Would have been warmer in the room. For reference, those same 21 steps can be taken forwards, starting with the pattern that I generated and just iterating it forwards in like a few milliseconds. So what makes this problem so ridiculous? I don't want to get into the forwards Game of Life too much because there are so many really awesome videos. I'll link at least one of them up here that you can watch to learn about the forward Game of Life because it's cool. But if you're unfamiliar, here are the rules. To travel from one iteration to the next, any live cell with either 2 or 3 neighbors remains alive, like this cell or this cell or this cell. Any living cell with fewer than 2 neighbors dies of underpopulation, like this cell. Any living cell with more than 3 neighbors dies of overpopulation, like this cell. And any dead cell with exactly 3 neighbors comes to life, like both of these. All the rest of the cells that start dead either have too many neighbors to come to life or too few. So from one iteration to the next, they remain dead. I like to shrink these 4.5 rules down to 2. It feels a little redundant to describe the cells that die when you can build up a new board from scratch by retaining some cells and adding some cells. Having as few rules as possible that you can state in the simplest terms possible also makes the computation a lot easier later on. So really it's just 2 rules. 2 rules that describe how one iteration moves to the next, control all of the amazing complexity in the structures formed in Conway's game of life. Because there's such a hard and fast set of rules that reliably advances one pattern forwards in time, you would think that there is a different hard and fast set of rules that takes a pattern and advances it one step backwards in time. But there's not. There is no way to reliably compute this pattern when you start with this pattern. In fact, if we put a random pattern over here, just a random arrangement of pixels, we can't even be certain that a previous pattern exists, let alone being able to compute that pattern in a reasonable amount of time. If you watched my video a few years ago about using a Monte Carlo algorithm to gerrymander the state of North Carolina, that was a comparatively easy computational problem to solve. So I'm going to try to explain why the reverse game of life is so much more difficult than gerrymandering the state of North Carolina. And to do that, I'm going to start by explaining how I like to think about these problems as a search through a high-dimensional configuration space, or if you want to get really fancy, a configuration hyperspace, which is really not as scary as it sounds. So this part of the video may seem like it's a little bit out of left field. This whole configuration space thing may feel unnecessary, but I swear it's not. Configuration spaces or phase spaces or whatever you want to call them are really important, and that's for at least 2 different reasons. The first off is just general scientific thinking. No joke, the other day at work, somebody proposed skipping an experiment out of a long sequence of experiments, and in agreement, I pointed at the ground, said, oh, there's our phase space, and then mimed taking like a really big step forward, like we're skipping all of these experiments that would be in this other part of the solution space. And they laughed. Now, they may just laugh because they're humoring me at this point, but they at least knew what I meant. So this sort of thinking in phase space, or this very large space of possibilities, is just sort of how scientists look at problems. The second perspective that's really important is computation, computer science. All of these large language models, these like AI things that are coming out now, depend on ridiculously highly dimensional spaces. Like a space that you're filling up that has thousands or tens of thousands of dimensions, and the weird math that shows up in spaces like that really allows these models to work. So being able to conceptualize these structures, even if you can't visualize it perfectly in your head, is becoming more important kind of by the day. Anyway, I hope you enjoy this segment. I'm going to zoom out and get very abstract for a little bit, but let's start by imagining that our entire grid is only 1 pixel. In this game, there are only 2 states. Our single pixel can be alive or it can be dead. There are only 2 game boards that can ever exist. The game board with the living pixel and the game board with the dead pixel. We can imagine walking between these 2 boards on a path that connects them. Not super exciting, but that's the absolute simplest case. So let's add the second pixel. Now we have 4 possibilities. Both live, live dead, dead live, and both dead. If we arrange all of these possibilities in a square, we can again connect them with paths. And if we do this cleverly, every time we walk on a horizontal path, we're flipping the left pixel, and every time we walk on a vertical path, we're flipping the right pixel. This is a configuration space. We've mapped all 4 possible configurations onto a 2-dimensional space that we can walk around in, and each dimension we can walk in corresponds with one thing we can change in the configuration. If you're following 3 Blue 1 Brown's fantastic series on how large language models work, this is very similar to the latent space, where directions have meanings and words or concepts have specific locations in that space. In this case, this direction controls this pixel and this direction controls this pixel. Let's add a third. Now that we have 3 pixels, That means we need a third dimension to correspond with flipping that pixel state. We've already taken up and down and left and right, so how about in and out? With a 3-pixel system, we have a 3-dimensional configuration space. 8 different configurations that can exist. And we can drop each of these configurations on the vertices of a cube. Even though it's much messier than before, every time we walk down one of these paths, we only flip the state of 1 pixel in the system. And every time we're walking on one of these 4 new paths, we're flipping that new 3rd pixel. I hope that's making sense, because it's about to leave the realm of easy visualization with 4 dimensions, and I tried to make a model. To go from 1 dimension to 2 dimensions, we took our line and we extended that line in a perpendicular direction. So we turned it into a square. To go from 2 dimensions to 3 dimensions, we took our square and we extended that square in a direction that was orthogonal to both of the directions that we'd already used to make a cube. Now you need to think about duplicating that cube by pulling it into a new direction that is orthogonal to x, y, and z. It's not an easy thing to imagine, and it's not something that can truly exist in our 3-dimensional space. But I did try to make a hacky model. To make this model, I took the original cube and extended it in a new direction so that we have 2 intersecting cubes. If you imagine that all 6 of these angles are 90 degrees, we have a hypercube, or a tesseract, or whatever you want to call it. It's a 4-dimensional box with 16 corners that contain the 16 possible configurations of a 4-pixel system. Now our configuration space is large enough we can start to see some interesting things. If we start with this particular configuration, that places us here. Now we have 4 available paths to walk down, and each of those paths would change a different pixel. All of these adjacent patterns are then very similar to the pattern we start with. But if we look at a different pattern, say this one all the way over here, it's very different. There are 3 pixels different between these 2, and that means that we have to take at least 3 paths to get there. We could go 1, 2, 3, we could go 1, 2, 3, we could go 1, 2, 3, but in any case, we're switching 3 pixels. We have to walk down 3 paths. These patterns are not just very different, they're actually far apart in configuration space. Plotting a system out like this actually sorts our configurations in a useful way. It's also important to note, because this is now a 4-dimensional thing, that there is some weirdness. These 2 nodes are actually opposites of each other. It takes 4 steps to get from one node to the next, but physically in the model, they're very close to each other. This is an artifact of making a 4D thing out of a 3D thing. If you look at a cube drawn on a 2D piece of paper, you could also say that these 2 corners look very close together, but they aren't, because you can imagine they are separated in the 3rd dimension. Imagining points like this can be separated in a 4th dimension is the big leap here. All these connecting rods are the same length, and to get from this position to this position, we need to walk down 1, 2, 3, 4 paths. And since you can only walk down these paths, these 2 points are actually quite far apart. If we add more and more pixels, the configuration spaces get impossible to properly visualize. This code is just sort of haphazardly cramming the extra dimensions onto a 2D drawing, but when I think about it, I normally just imagine like a huge mess of dots connected by paths, and nearby dots are similar to the one you're standing on. You don't really need to be able to think in hundreds of dimensions to get some useful intuition out of this. So if we choose a node at random, we're probably going to find something that's blue or green, and then we can take steps until we get to redder and redder nodes, and when we get to the reddest node, that's all live pixels. That's 1, 1, 1, 1, 1, 1, 1, 1, whatever. If we wanted some other pattern like this, we could recolor all of these states and then do the same thing. Drop in at a random location and keep taking steps, flipping 1 pixel at a time every time we walk down one of these paths, towards redder and redder nodes on the graph until we reach the desired configuration. In order to reach this configuration, you theoretically never have to take more steps than the number of pixels that there are. If you've got a 30 pixel system and the state you're looking for is the exact opposite, where every one of those states has been flipped, you really should only have to take 30 steps if you know which steps to take. If we have some very complicated problem we're trying to solve, say that we're trying to find nodes that represent valid backward states in the game of life, this coloring problem becomes extremely computationally intensive. If you imagine yourself an algorithm trying to solve this problem, that means you're traveling blind. You know what your destination looks like, but you have no idea where it is or how to get there. You might start with some random configuration, look in every direction, take a step towards a slightly better solution, look in every direction, take another step towards a slightly better solution, rinse and repeat. In an ideal world, this strategy gets you to the answer, and you've only had to check a small fraction of the total possible solutions. This is the best case scenario. This is how you write an efficient algorithm. But while we're looking at this visualization, think about what you'd do if you followed this routine and then suddenly you found that all of your available options were somehow worse than where you were. Would you just take a random step? Would you call the problem solved? If you can't see the whole map, you're gonna run into some messy quandaries. We could not possibly evaluate every node on the ridiculously large graphs that we would need in order to check every previous state and find a good one. That's why the path that you take through phase space really matters, because it needs to be efficient. You can't look at the whole space at once. Now, some computational problems are more likely to get you stuck than others, and before I talk about the game of life, I want to talk about an easier problem, drawing maps. I started on this game of life project about a month after releasing my gerrymandering video, where I had used a Monte Carlo simulated anneal algorithm to evolve election districts on a map of North Carolina. And that configuration space was enormous, but it was very nicely, sort of smoothly shaped, which actually made it a very easy problem to solve. In a simple version of the map drawing problem, let's say we have this map with a large city in the middle, and we need to cut this map into two districts that have equal populations. We could do that like this, where each district takes half the city, like this, where each district takes half the city, or like this, where there's a city district and a rural district. All of these configurations are valid solutions to the problem, because in all of these cases, both districts have the same population. This is an example of a poor solution to this problem, where the districts have mismatched populations. Now I want to try to come up with an intuitive configuration space, just something that helps us think about this problem. But because this map has 36 pixels on it, and each of those pixels can have two different states, we don't really want to draw 68 billion nodes on a 36-dimensional grid. We need something that's a little more parsable for humans. At least for this simple system, I would hazard a guess at flattening this massive graph into 2 dimensions, something like this. Obviously, there are many ways to imagine this space. This is just the first that came to mind for me. You can also think about this as a height map, which makes the phrase gradient ascent make a little more sense, but we'll get there in a minute. The case where the city is green and the rural areas are yellow is here, and the opposite case where the city is yellow and the country is green is over here. These are opposites of each other. Every single pixel, the entire state has been flipped, so we want them to be far apart in configuration space. If we walk away from either of these solutions in any direction by flipping a pixel, we unbalance the districts, and that makes our answer a worse solution. In the configuration space that I've drawn here, I've used this color map to show basically how good the solutions are. Both of these points are the dark red. They work exactly, but changing them at all, taking any step in configuration space in any direction, makes these solutions worse. Now, as we flip pixels on our map, we can walk around this space, and in order to solve the problem, we need to be in one of the red regions. If you're trying to write an algorithm to do this, it's really easy because the graph is smooth. You drop yourself anywhere in configuration space and walk uphill. If we start here, we have a very lopsided solution. We can see on the configuration space that it's a bad solution, and if you just look at the map, clearly the districts are unbalanced, so it's a bad solution. But if we just start flipping pixels and checking if any given change gives us a better map, then we can keep it. And maybe we try to flip another pixel and it makes it worse, so we don't keep it. Incremental changes bring us closer and closer to a solution, and this is really important. Because this configuration space is smooth, every single time that we take an incremental step that makes our solution slightly better, we can be very confident that that step is also getting us closer to a global solution, a configuration that actually answers the question. In this case, the algorithm is really easy, and that's what I was doing in the other video 3 years ago. Now at the other end of the spectrum, here's how I imagine the configuration space for a reverse game of life board. This space is messy. It's covered with local maxima that don't actually solve the problem. I've only drawn 3 actual solutions here, and the rest of the terrain is just stuff that's in the way that you've got to deal with. It's possible that we choose a starting condition, walk incrementally uphill by flipping 1 pixel at a time, and solve the problem. But it's a lot more likely that we start somewhere, walk up a hill, and then realize that the hill isn't tall enough. We will get stuck circling a false solution. So what do I mean by false solution? I had to dig back in the files, but this was my very first attempt to solve the reverse game of life problem before I realized that the phase space was a mess. And I approached it the exact same way that I had just finished approaching the map drawing problem. Spoiler alert, this is not going to work. This starts with a random configuration of pixels and then tries to flip those pixels one by one until it finds a change that improves the solution. When you take our random guess and you iterate it forwards 1 step in the game of life, 31 cells in the resulting image are alive or dead in the wrong direction. If we let this algorithm continue for a while, we see that it moves forwards. Our reconstructed image here is getting closer and closer to the target. But eventually, if we let this continue, it gets stuck. Here there are only 9 cells incorrect in the answer. We are replicating most of the pattern that we want to replicate. So this is a much better solution than the one that we started with. But solving the reverse game of life is an all or nothing thing. You don't get points for being close. And this simulation is stuck. I let it run for a bit longer after this, but it never moved again. If we take this guess and plot it on some configuration space, it's at a local maxima. There's no way for this algorithm to advance because it's already walked uphill as far as it can. If we change this pixel, for example, we can see that we've made this cell look like the target. But in doing that, we've broken all of the rest of these cells. Even if changing this pixel is something that is necessary to find a global solution to this problem, it's not a step that this algorithm will take because it always wants to try to optimize. If you remember, there was a similar problem that I encountered in the gerrymandering video, and we solved it by randomly taking random steps in the configuration space to sort of jump away from these local maxima. But this simulation was actually already running with randomness thrown in, and it's not enough to get us to an answer. Adding random noise can sort of help you avoid potholes, but it won't help you if you've climbed the wrong mountain. My next bunch of attempts are basically mildly more intelligent versions of this same algorithm. I tried to implement the random steps in smarter ways. I tried things like having it progress from one side of the screen to the other so that when it took random steps and sort of locally nuked the simulation, it wouldn't destroy solved progress. But even after all of that, I think that I got this algorithm to find a solution like maybe once or twice on very small systems. This was not something that I could use to efficiently take many steps backwards in time. What we really need is an algorithm that looks at the configuration space, climbs to the top of a hill, and if that hill isn't tall enough, crosses the entire thing off its map to explore elsewhere. We need something that's more intelligent, and for that, I asked Reddit. I don't know why I asked Reddit for something more intelligent, but I did. And then somebody on Reddit recommended a magical package called Z3. There is a class of problems in computer science that are said to be NP hard to solve. Technically, this means that no known algorithm can solve them in polynomial time. Say we were trying to figure out a backward step in the game of life on a grid of 4 pixels, and it takes a certain amount of time to solve. If we try to solve a grid of 8 pixels and it takes twice as long, the problem is linear in time. The amount of time to solve the problem is directly proportional to the number of pixels in the grid. If we try to solve our grid of 8 pixels and it takes 4 times as long as the grid with 4 pixels, then it's quadratic. The time to solve is proportional to the square of the number of pixels. It can be expressed as a polynomial of the number of pixels. NP hard problems, like the reverse game of life, are actually non-polynomial in time. Their compute time grows faster than any polynomial. So when you're looking at larger and larger systems, we very quickly get to the point where we can't compute anything. However, there is a space, however small, that we can work in. The specific problem we're going to talk about in a minute is part of a subset called NP complete, which means it can be solved in at most exponential time. In a realistic scenario, there may be some setup time for the computation. There might be a constant for how fast we check each result. Another constant for how efficiently the algorithm searches configuration space. And then there's the exponential bit that grows obscenely fast. Because of that exponential bit, we will eventually hit a wall. If we have too many pixels, we're gonna have a bad time. But there's nothing saying we can't make these constants as small as possible. In a way, this is only delaying the inevitable, because eventually the complexity will explode. But it means we have at least a theoretical path towards solving small systems. Enter SAT solvers. And the mother of all NP-complete problems, Boolean satisfiability. Like, literally the Wikipedia article has a picture of a SAT problem as the first thing under NP-completeness. The cool thing about all these NP-complete problems is that they're basically equivalent. If you can't solve one, you can't solve any of them. Or in this case, because somebody solved one, maybe I can get them to solve this other one too. The first description of a satisfiability question that I heard, and still my favorite, was an example about seating at tables for some big event like a wedding. Here we have 12 guests. Alice, Bob, you always have to start with Alice and Bob. Then we have Chuck, Dave, Elaine, Frank, Gort, Hiccup, Inigo, Jessica, Kay, and Lewis. Now we have two hexagonal tables, and we need to distribute these 12 guests into two tables. But we also have a list of requirements. Alice and Bob, Jessica and Kay, and Elaine and Frank are couples, so they have to be seated together. Cool, that already works. Gort and Hiccup are Elaine and Frank's kids, so they need to sit together as well. That means we need to do some rearranging. Let's exchange Gort and Hiccup for Chuck and Dave. That way the whole family is at table 1. Next, Inigo needs to be at the first table to initiate a toast partway through dinner, and either Dave or Elaine needs to be there with him. So let's displace Alice and Bob so we can move Lewis and Inigo to table 1. Now we have a problem because Dave and Bob can't be at the same table. They have some sort of feud that's persisted since college, and you haven't wanted to bring it up, so let's send Dave away to table 1. Also, on top of all the rest of this, you need to make sure that Dave, Elaine, and Inigo aren't all at the same table, because they really all like to talk about obscure computer science problems, and you don't want the other guests getting bored. But you know that they won't really get going unless all 3 of them are together, and we can fix that by exchanging the families. Now we're to the bottom of the list of requirements, but if you look, along the way we've broken one of our earlier rules. Dave and Bob are back at the same table. One more exchange and we've sorted it. Now all conditions are satisfied, it's a satisfiability problem, and dinner can begin. Also, I didn't want to bring it up, but implicit this whole time has been the requirement that each table has 6 people at it, which could look like this if you assume we're using ones and zeros to describe the rest of these variables, but if we're using trues and falses in Boolean logic, it's a real pain to say that exactly 6 people have to be at each table, and that looks kind of like this. Solving this problem is actually an NP-complete affair. There is no simple way to do it. There's no algorithm that you can use to walk down this list and make sure that you put everybody at the right table. You're always liable to make a mistake, and when you make one update, it's going to send you backwards, and you'll have to fix something else. The next time that you have to plan a dinner for a lot of people with complicated requirements on seating, or any of the other equivalent NP-complete problems, is that other people have written solvers for these things that are really great. And if we can find a way to rephrase our question in terms of math, in terms of all these Boolean conditions, then we can use this SAT solver that somebody else wrote to very efficiently chug through all the combinations, walk through phase space, and find an answer that works. Now these solvers are not magic. They feel like magic, but they're not magic. They are still limited by the fact that this is an NP-complete problem. They're still going to be exponential in time. This would be useful if you needed to sort like 100 party guests, but maybe not if you needed to sort 20,000 party guests. So this method works really fast. The people that wrote Z3 actually know what they're doing, and they rearrange all the pixels in my game of life drawing, sprinting at maximum speed, hiking across phase space, looking for only the tallest mountains. If you really want to understand how SAT solvers work under the hood, I'm not the best person to answer that question, but I can recommend this video and the videos that I've linked in the description down below. The simple answer is that they take guesses, like we did when we put all of the different people at different tables, but then they actually add new constraints based on what they find. For example, when we had 4 logical statements that together listed the fact that Gort, Hiccup, Elaine, and Frank needed to sit together, a good SAT solver would have realized that those statements are redundant. We can cross this one off and simplify the problem, because when the rest of these statements are true, so is this one. Likewise, a good SAT solver could add new requirements if it realizes that it helps narrow down a problem. When Dave and Bob couldn't be at the same table, but Alice and Bob needed to be at the same table, maybe in the solving of the problem, it turned out to be more useful to say that Alice and Dave couldn't be at the same table. Using changes like this, a good SAT solver can very quickly eliminate large swaths of the possible solution space at once. A SAT solver looks for logical inconsistencies, and when it finds a logical inconsistency, it can use that to throw away a large group of possible solutions, limiting the number of solutions it needs to try before finding one that works. In the case of the game of life, a SAT solver may try to solve a small group of pixels, realize there's no solution possible if this pixel happens to be alive, and generate a new constraint. This pixel must be dead. And then when that propagates through the rest of the constraints of the game, crosses out a whole bunch of logical statements and makes the solution easier to find. From my perspective, just using Z3 as a library, the tricky part is how to translate, how to take the game of life and make it into weird mathematical gibberish. I actually did this translation step in a bunch of different ways. Z3 can do more than just Boolean logic, so my first attempt started by using integers for every pixel. I said every pixel had to be 1 or 0, but using numbers like this let me put in an intermediate layer that said how many living neighbors surrounded each cell. I was building a 3-layered structure with the final state, an intermediate sum level, and the previous state that I actually wanted to compute. Once we've done this for every cell in the simulation that we want to solve for, we have a list of hundreds or thousands or tens of thousands of separate logical statements. And this list is what gets fed into the Z3 solver. We played musical chairs with fewer than 10 constraints. It gets to play musical chairs with this. And thankfully, it's really good at it. I'm not really sure how Z3 makes its initial guesses, but there is some randomness involved. If you run the same code multiple times, you could get different answers. The fun thing about these solvers, though, is that you can just keep adding constraints. If I run this code and generate a possible step backwards from this glider, we might get this output. But that's not the previous glider step, that's just another way to make a glider. We can input all the exact statements again, and then at the end we say, oh, and by the way, you're not allowed to make this state that you already found. And when we run that, we guarantee that it will find a new solution. Then we can do that again, and we can do that again, and we can do that again, and eventually it fails to solve. This means that within the constraints that we've given it, with like the sizing and how many pixels are allowed to change and stuff like that, it has found every possible solution. So behold, these are all of the ways to make that pattern, with only nearest neighbors of previously living cells allowed to be in the final solution. Now, taking multiple steps backwards feels like it should be child's play at this point. We can take one step backwards. What if we just take one of these simulations, bring it over here, and then run the Z3 solver again? Well, we can do that, and then we do it again, and then we do it again, and then we do it again, but, oh, wait, it broke. Yeah, so eventually it stops solving, and then there's an entirely new set of problems. So that's going to be a topic for next time, but it involves trying to avoid states called Edens. It involves a significantly more meta phase space where we're searching through a space of valid solutions for solutions that give us more valid solutions. It's a real mess. The animation that you saw at the beginning of this video, I think consisted of 3 or 4 individual SAT solves, 2 of which took over a week to compute, a single SAT solve. These aren't the SAT examples that I've been showing here, where you can click it and it'll find a solution in like 5 or 10 seconds. It ends up being significantly less straightforward. I clearly get obsessed by mathematical puzzles like this, and how to think about them and how to visualize them. But however much I try to make my videos understandable, they're still just videos. You can't change the videos. You can't change the animations that I've done. And I can tell you from being able to play with the animations that I've made for these videos, that really helps. But here's a visualization that you can play with, which is absolutely the better way to learn. Here's a lesson teaching you to think in multiple dimensional space from Brilliant.org. It's a live visualization, and you get to fiddle with all these knobs, which is amazing. I actually really like this question too. It's not asking you to accomplish the task of lining up with the dot with the arrow. It's asking if the task is even possible, which really makes you think about the problem and the variables you're given. I've actually blurred out the details of the variables that it's giving you here so that I don't ruin the surprise. You should go try this one. It's informative and it's really fun to fiddle with. Here's another great one about machine learning. Here you're learning to manipulate individual neurons in a neural network to learn how activation functions work. Visually, it's fantastic. Brilliant has lessons in a huge variety of topics, extremely relevant to what I've done here today. Programming, logic, math, AI, and if you like learning this type of stuff, you need to go check them out. In my mind, it's a perfect next step after a video like this one. I try to get people excited about these types of questions, but you can't really learn something and internalize it without doing it, without trying out some problems. And that's exactly what Brilliant lets you do. So if you want to try everything that Brilliant has to offer free for a full 30 days, check out the link in the description. Thanks to Brilliant for supporting this video, thanks to you for watching, and I'll see you next time when we take multiple steps backwards in Conway's game of life.